All right, folks, who's ready to learn about the structure of the nervous system? How many of you were here last week? I mean, I know you were here because I keep attendance. How many of you thought last week we talked about structure of the nervous system? Yeah, very similar titles, right? That was kind of like what we call fine structure, or like cellular structure. We're talking about something a bit smaller. Today we're going to discuss sort of a broader structure of the nervous system. I hesitate to tell you not to take notes today, because some of you are going to take that as like an excuse to, I don't know, like shine your shoes, or pluck your eyebrows, or whatever it is you do in class that other than pay attention. But what I really want to get across to you is today is really sort of this chapter is going to be more of a framework chapter, right? So don't try to write down every single detail about every single brain region that we talk about. The reason for that is we're going to talk about all of these brain regions later, right, as we get to those appropriate systems. So today is really sort of an introduction, right? Here's the hippocampus. It does stuff with learning and memory. That's what I want you to walk out of with here today, okay? In 8 weeks, when we talk about learning and memory, you better be able to tell me about NMDA receptors and calcium channels and LTP. You don't need to know that today, okay? Because I can't fit everything in today for a 16-week semester, all right? So this is kind of a framework day. I'm just going to introduce you to a few places so you guys can get acquainted.
Are you recording?
I believe I am. But I should confirm that, right? There you go. Does anybody listen to these lectures? No? Anybody has listened to them, but they don't want to be that one nerd that raises their hands? Okay. I just want to check the audio quality to make sure it's okay. That's all I need. I don't really care if you watch them or not. It's not any effort on me, even if you're the only person who ever watches it. Okay? But I do have 67 subscribers. So watch out. Taking the internet by storm. All right, we'll talk some basic features of the nervous system. We'll briefly talk development of the nervous system. I try to really avoid development of the nervous system. I just try to avoid talking about kids in general. So that's just, if we can do that, we will, right? Later I'll tell you guys how to avoid having kids, in case anybody needs to know how to do that. But that's a chapter like chapter 10 conversation, okay? So hang in there. I know it's going to put a damper on your social life for a few weeks, but we'll get it straightened out. We will talk central and peripheral nervous system. We'll talk a few things. I'll tell you what's important as we go. How many of you know directions of the nervous system? Great. How many of you don't know that? That's great too. I'm not going to spend any time on this. If you need to go back and sort of study these, please do so. I'm not going to, in the middle of class, go through some complicated conversation about whether something's dorsal or ventral to some other sort of structure. That's not really the point of this class. What this will help you do, though, is if we talk about the dorsolateral prefrontal cortex, right? That's like a big mouthful of stuff that you don't know, okay? But if you know, hey, I know the word dorsal, I know the word lateral, I know kind of prefrontal cortex, it'll give you an idea of where this thing is located. Might give you some sort of, kind of place to plug that in so you've got some grounding there. Otherwise, it's not going to be too important for this class. Hey, who's ever cut up a brain? Yeah, it's fun, right, Trevor? You don't have to answer that. You had to do it. That's awesome. Yeah, that's great. So sometimes you just get the urge and or the direction of your professor to cut a brain, right? Both of those are great reasons to do this. When we cut the brain into different planes, right, so we can cut this different ways, it gives us a different view of the brain and the brain structures. It's a very complicated three-dimensional sort of structure, so we want to think about those things as we're doing that. We've got what's called a cross-section frontal. Most of the time we'll call that a coronal section. Just kind of chopping down the front, cuts you into a front and a back. Horizontal, it's going to cut you into a top and a bottom. And then sagittal sections is going to cut you into a left and a right, because we're going to cut you down the middle. That's really all you need to know. When we do see the brain and we see it represented in the in images or models or online, we look at these things, we do want to think about how has that brain been cut, how are we looking at this, and why does it look different, right? Sometimes it's going to look like this. It's not horrible, right? Sometimes if you cut it down the side, it's going to look like this. Okay, and if you cut it top to bottom, it looks really weird. You got a big fiber bundle and some holes in the middle. I studied art before I went into brain science. Got really far. Right there in the 3rd grade, they kicked me out. There you go. There's that central nervous system again. We already talked about this. Central versus peripheral brain, spinal cord, definitely encased by bone. And you've got cerebral spinal fluid or CSF. And your peripheral nervous system are all those nerves and ganglia. Not a big deal. There we've sliced your brain into different sections. You can have an idea: coronal, sagittal, and horizontal. We need to think about this as we go through the spinal cord as well, right? Even though the spinal cord is thought of as a different sort of organ than the brain, right? And organization is a little different there. It's really just all continuous right here. You come out of the brain stem, go into the spinal cord. How do you know when you go from the brain stem to the spinal cord? Got one of those nice little signs for you that says now entering spinal cord, so you definitely know as you're traveling down where you are, right? There's some difference. When you get in the spinal cord, you're going to see kind of this. You've got fiber tracts on the outside, cell bodies here in the middle. You don't have a lot of other structures. If you're in the brain stem, you do have other structures that you'll see thymus, so you'll see other kind of clumps and clusters of brain cells here and there, okay? Not too much to worry about for this class. All right. Now this is kind of important. How many of you love alligators? Okay, some people, that's great. The important thing is to realize you are not an alligator, and I know that's probably the toughest lesson that I get today. And so you think, well, why, Bethany, is that important for my life to know I'm not an alligator, right? Well, the important thing to think about is what we call the neuraxis. And when we think about those words, dorsal and ventral, and we apply those, let's say, probably not to an alligator because there's not a lot of neurological research on alligators, right? There's not a lot up here going on, but there's a lot on rats. And rats and alligators walk the same way. And they walk by using sort of like 4 limbs instead of 2, right? So that's pretty awesome. That changes the orientation of their brain relative to their spinal cord compared to humans, right on? That makes sense, right? So when we talk about something that's rostral or anterior or dorsal or ventral, just keep in mind how the head's oriented to the spinal cord and you guys won't get lost. Questions about that? Okay. If you ever get confused about dorsal, just think about dorsal fins. If you ever get confused about ventral, just think about ventral fins. I'm sure that really helps. All right, who loves Meninges? Great, these guys are awesome. Your brain and the spinal cord, remember they're both the central nervous system, are surrounded by these protective sheath called the Meninges. You've got 3 of these. You've got the dura mater, which means tough mother. I don't know, it's kind of a, I don't know if you send that to your mom on Mother's Day coming up in May, right? Like tell her, wow, you're one dura mater. I don't know if that's, some moms will think that's funny. Some will just throw the card away. Depends on the relationship with you and your mom. Beneath that, you have something called the arachnoid. The arachnoid is it's called that because if you pull the dura up and it stays attached, it looks like these create these little sort of spider web sort of things. Trevor, when you were slicing through that brain, I'm not going to ask how you acquired it, but just leave that for a statement you'll make elsewhere. So when you were slicing through that brain, sometimes you will get brains that actually still have the dura attached on the outside. I don't know if the one you had did or not. It's like this really tough, like thick. It's almost, you think it's like almost not natural. It's so tough. You're like, why did they shrink wrap this in this opaque plastic, right? So anybody, human brain, sheep brain? Sheep brain, yeah, that's pretty standard. Sometimes it'll still be attached like down the middle of the sheep brain. There's like this like hard kind of piece you're pulling out and you're like, what is that? That's the dura, right? It's kind of this really tough structure. The last you have is the pia mater. This actually is interesting. It actually adheres to the surface of the brain. So your brain is kind of this, wrinkly surface like that. Your dura goes over the top of that so it can create this space, right? How many of you have heard of like subdural hematomas? Yeah, I guess where those are located, right below the dura, right? So that's kind of how it works. Your pia, on the other hand, is going to just fit right on top of all of those bumps and valleys, right? Which we'll learn the name of in just a moment. All right, you've got your CSF. Basically, this is blood plasma, but it's in your brain, right? We're not going to have to think too much about CSF or that subarachnoid space. You do have 4 ventricles. You've got 2 lateral ventricles. In the 3rd ventricle, you've got a little aqueduct between the 2 going to your 4th ventricle. Occasionally that gets jammed up. This particularly happens in kids, and you've got to put in a brain valve, right? So I don't know if anybody knows anybody with a brain valve. It happens. Don't worry about it. Right? Just keep it clean. I wonder if you can take it to the same place where they clean the valves in your car or something, to get your brain valve clean. I don't know. I think about these things sometimes. Here are your ventricles. You got your lateral ventricles there. They've got those horns. 3rd ventricle in the middle, and the 4th down there, close to your cerebellum and brainstem. All right, here's a kid with a brain valve, right? They put this big straw right there into the ventricle so they can drain the cerebrospinal fluid. It can get jammed up in there, right? If you think about your blood plasma, right? If it got jammed somewhere, if you had some sort of blockage, you kept pumping plasma in, but you didn't pump anything out, right? What's going to happen? Your arm's going to swell up like in a cartoon and explode, right? You don't want that to happen to your brain. One of the major problems with your brain, in a case like this, you would think, well, my brain's pretty squishy, right? Well, can't it just expand? And it most certainly can, right? The problem is that thing outside of your brain called the skull, that one doesn't expand very well. I don't know if anybody's ever tried to change the size or shape of their skull. It doesn't work very well, right? It involves a lot of Dremel tools and some stitching, okay? So don't give that a go. So when you run out of space in your brain case there, right, you start to put pressure on the brain tissue itself, and that can cause a lot of mechanical damage and brain damage. So instead, we put that nice little valve, drain this down into your abdominal cavity, and just absorb that. That kid also needs to look at a glass of water. I don't know. Okay, so let's think a little bit about development, right? How many of you have ever developed a central nervous system? Yeah, most of you have, right? Again, we'll know when the midterm comes around which of you didn't, but that's okay. It's never too late to start trying. So, central nervous system starts pretty early in your embryonic life, and it's really just this hollow tube, right? So you just kind of have this hollow tube up the middle with some neural tissue wrapped around it. Essentially, that's what your adult nervous system is, right? If you think about your brain and your spinal cord, you put those ventricles in there, and then you've got a hole going down your spinal cord too, right? And it's full of CSF. So really, you're still dealing with a hollow tube, even once you're an adult. Although you got this big bulge on one end, right, that you use to fill up your skull. So that tube during development elongates, you get a bunch of pockets and folds, and eventually you get a brain. So there you go. That's the sort of developmental stages of your brain. I would advise not screwing around with that, right? Okay, because there are a lot of things we'll talk about later that can happen, right, during this developmental process. It's a very delicate, time-sensitive process, right? And even small tweaks in this process can have profound effects later. And we'll talk about some of those as we go along. There are different parts of your brain. I know it's a real shocker. You should write that down. That'll be on the exam. There are different parts of your brain. And they do different things, right? They start out pretty early in those different segments, and then later they develop in the different parts, structures of your brain. There are a lot of folks who will make you study these divisions and locations of ventricles and subdivisions and such. I think those are people who will waste your time. I'm not one of those. So, you don't have to worry about sort of these things. I do want you to think, though, about some of these main brain structures, right? And again, we're going to think about them lightly today because we're going to hit a lot of these in detail later, okay? How many of you have heard of the cerebral cortex? Yeah, that's a place. Yeah, there you go. Good job, Brandon. What about the basal ganglia? If you've not heard of the basal ganglia, you've heard of problems with the basal ganglia. How many of you have heard of Parkinson's disease? Yeah, that's a problem with your basal ganglia. Limbic system. Okay. Again, if you've not heard of it, you've heard of people who have problems with their limbic system. They're called overly dramatic. So that's kind of that was a good one, right, Casey? Write that down. I'll try that again. Casey's back there keeping notes for me for my one-man show next semester. We've also got the thalamus. That's a real sensory processing station. Hypothalamus. This guy is super important. In fact, you might hear me sometimes say the hypothalamus might actually be one of the most important brain regions ever created, right, through evolution. The reason for that is it controls so many hormonal processes which control behaviors. It's just got a massive influence on your development and your behavior. It's kind of cool. Don't worry about tectum, tegmentum. We will talk about the cerebellum a little bit. So there's some cool stuff going on with the cerebellum lately. Some new research, but mostly we think about it with motor coordination, which is kind of cool. And then you've got some other brainstem structures, things in the hindbrain. I call that the idiot box. That's where we put things that you're not supposed to screw around with, right? So we put important things there that if you were responsible for it, you'd be dead, right? Like heart rate, blood pressure, breathing, right? Thankfully, we don't have to consciously go, all right, heart, go ahead, keep pumping, well, we'll do one more. And then you think, oh man, look at that awesome video game, and the next thing you know, you're dead because you forgot to make your heart beat. It happens. I've seen it. Right in front of GameStop, piles of bodies. Hey, who loves the cortex? Brandon, you're going to be our cortical expert. It's pretty cool, right? It's that big wrinkly thing on the kind of the outside of your brain. This is really what separates, well, mostly what separates you from a rat. Okay? Rats don't have a whole lot of cortical stuff going on. They got like a smooth marble up there, right? Not a lot of business going on. We've got nice wrinkles. It's all kind of fun. Fun things. I guess I should take a moment. I always like to sidestep and do a little myth busting. Right? Because we should do this as we can. How many of you have ever heard, like, every time you learn something, your brain gets a new wrinkle? People hear it. It's fine if you heard it. I didn't ask if you believed it. That's a separate situation. Don't raise your hand for believing it. That's not really true. You got all the wrinkles you're going to get up there, right? And that's what's going to happen. And it's not really indicative of individual learning, right, at that level. It's just sort of a proxy for the complicated cortical development, but that's not even 100% accurate. When we do talk about cortex, we'll say it has 6 layers. That's kind of important. We'll talk more about that later. I'm going to ask you a whole lot of information about inputs and outputs. Just know some layers handle information coming in, and some layers take that information and send it elsewhere. That's really what's important. Early in development, you don't have as many layers, and eventually you get up to 6. Megan, there's a real problem with this. This was developed, like, let's say 100 years ago, right? And guess what we had 100 years ago? Well, I guess we still have these. Guess what we have now that we didn't have 100 years ago? Better microscopes, right? So, and better visualization techniques. So somebody took a look at the cortex and they're like, oh man, that's got 6 layers. And that was awesome. And they got all kinds of like real, praise and publications and probably like institutes named after them and fun stuff like that, right? And then some guy came along like a couple decades later and was like, hey, yeah, there are 6, like, but plus 2. So what are we going to do here? And they're like, man, we've already named the cortex with 6 layers. We're not going to change that. I don't know what that was, Jacob. Sounded like a fire alarm at first. Yeah, that's what I wasn't waiting on you. I was going to be going. Spraying water in front of me. You guys are on your own. So, and somebody's like, well, layer 4's got like some extra layers. Are we going to make like a layer 6, layer 7, 8, whatever? Like, no, why don't we just go like a 4A or a 4B or something like that? So, Cortex has 6 layers plus some other sublayers, right? Sublayer is not necessarily any more or less important than anything else. It's just, well, we didn't figure it out the first time around, but 6 is a good number, so we're not going to change it. Okay. Sort of a historical holdover. All right, prenatal brain development. Progenitor cells are kind of cool, right? Those are awesome. These are those stem cells that can turn into fun stuff, like whatever they want to, right? They're like you as a child, and you're like, what do you want to be when you grow up? Kids are like, oh man, I'm going to be a dinosaur. Like, yeah, you can do that. That's fine. Those are progenitor cells. Don't have so many of those once you get to be an adult. You have some in a couple locations. We'll talk about those as we need to. We have complex brains. Our brain development takes longer. We talked about that. You guys remember that fun neoteny stuff that we discussed previously, comparing humans to horses, right? Horses get up, they take off running as soon as they fall out of a uterus. Humans, that's not the case. It takes them decades before they're up doing things on their own, right? How many of you in the last 3 years had your mom make you a peanut butter sandwich? There we go. That's what I mean. Yeah, humans, we're not so great, right? It takes us a while to develop. There is this process of overproduction and refinement, which is kind of cool. And sometimes we refer to this as synaptic pruning. You guys remember we talked about synapses last week. When you are younger, you'll actually have more synapses than when you're an adult. Doesn't mean you're brighter or better when you're younger. It actually means you're sort of worse and wired up incorrectly, right? So you've got all these extra synapses. You don't use those. Guess what happens? We chop them off, right? Make a nice sort of beautiful arrangement. Anybody have a bonsai tree? Anybody into fancy shrubbery? You make it look like a giraffe? No? I'm surprised. I thought that was a big hobby amongst college-age students. So, what we wanted, Casey, is that not, must be reading the wrong publications. Write that down. So, basically what we're doing here is we're eliminating things that we're not using. This is why, like, if you grab a kid by the leg, I don't know, like their other arm starts to twitch, you don't know what you're doing, right? You just like poke kids in the stomach and weird things happen. I saw it on a YouTube video. You get rid of the synapses that you don't need as an adult, right? If you don't get rid of those, you can develop some problems. Of course, you don't want to get rid of too many. That's another problem, right? So you got to kind of ride the line there.
Does that do with autism? Does autism have less synaptic pruning?
They do have, yeah. So we could have a whole conversation.
Like overstimulation.
Yeah. So we could talk about autism, and we will later. But folks with autism don't tend to go through this same sort of refinement process. So if you were to kind of chart that, and you kind of have regular synaptic pruning, folks with autism tend to, you can't see that, tend to sort of overproduce and they stay. They do lose synapses as they get older, which happens to everybody, but they lose them at a slightly different rate based on at least what imaging techniques we have available to us. It's kind of an interesting situation. All right. Patterns of development, obviously genetics plays into this, personal experience, and those can influence how you create cells and how many you create. All right, there's sort of just a graphic of synaptic pruning. From birth to 6 years, you're kind of building up, and then you start to trail off as you get a little older into adolescence and adulthood. Don't need to know too much about that. You don't know anything about this. All right. Let's talk about specific brain regions and brain structures in general, what they're doing, and then later we'll pick up details. All right, you've got this thing called the forebrain, and that really gives you a ton of information about what it does. All it means is it's the front part of the brain, right? Doesn't really tell you anything that's going on there, but it's the front part. It's got some weird thing called a telencephalon and a diencephalon. I'm not going to ask you about that. Don't even waste the ink or pencil lead to write those words down, okay? You do have your cerebral hemispheres. That's really what's important up there, right? You got these two kind of wrinkly walnut-shaped things on either side of your brain, okay, left and right hemisphere. We will talk about what each of those hemispheres are doing. They're not identical, right? They do slightly different things. We'll talk about those hemispheric lateralization or lateralization of function later. Who remembers those nice little valleys that we talked about, right? Remember we said we had those wrinkles, kind of the ups and downs, right? If it's a valley, we call that a sulcus. If it's plural, it's sulci. If it's a bump, we call that a gyrus, or a gyri if it's plural. If you get a really big sulcus, we call it a fissure. Not a whole lot you need to take away from that. Species with more complex brains tend to have a higher number of sulci and gyri, right? Because we're trying to cram more cortex into our brain case, right? So if you think about humans, humans have very wrinkly brains. I already said rats really don't. They're super smooth. There are a couple caveats to that. One of those are sheep, right? Trevor knows, he's our sheep brain expert. They have wrinkles, right? And those kind of little dips and valleys. One or two, yeah, they got a few, but they're not so bright, right? I mean, sheep are not known for their intelligence. Nobody says, man, watch that sheep do a calculus problem. It doesn't really happen, right? They're not known as the geniuses of the animal kingdom. So, sulci gyri. You do have a spinal cord. That's kind of cool. You got a thing called a cauda equina. That's the horse's tail down at the bottom. Spinal cord doesn't go all the way down, right? It goes down part way, stops, and all your nerves have to jump off. That's cool. You've got a thing called the filum terminale. That's what holds your spinal cord down, kind of like a string on a blind, right? You got it nailed down there. Don't try to knock that thing loose. That's a bad idea, right? So you have to walk carefully. Actually, it is a problem if that breaks, and it can, right? Your daily activities aren't going to make that happen. But if it does, then your spinal cord might actually start to shift up a little. You can shear off your spinal nerves. Sounds bad, right, Dylan? It is. All right, cerebral cortex. Cerebral cortex has probably somewhere between 4 and 10 million brain regions, right? Some number in there, right? There are a lot of them. They all do different things. They're all related to different processes. I'm not going to ask you to memorize all of them. The real problem is there are like 8 different naming systems for the same brain regions, right? And that gets confusing as well. So in cortex, we want to think about things like primary visual cortex, right? That's a spot where you're getting a bunch of visual information coming in. That makes sense. Primary auditory cortex, it's a real shocker. That's where auditory information is coming into your brain, into your cerebral cortex. Primary somatic sensory, it's body stuff, right? Body senses. Primary motor cortex, now this one is mixing it up a little bit. That's where you're sending information out, not getting information in, right? So it's going the other direction. Crazy thing about this primary visual cortex, so we call it primary visual cortex. We might also call it striate cortex, right? We could also call it V1. Brodmann's area 17, right? So you got all these kinds of labels that you can put on there. Don't get too worked up about it, right? They all do the same thing, just put different names on it. Some guy thought he had a better naming system than somebody else, and then he kind of forced the people to go that way, and then, I don't know. We didn't kick anybody out. We probably should have. Probably should have said that's wrong. Here's the right answer. There you go. And then, Megan, someday we can have a conversation about how we name things in other species. That's really well. Because every species has like its own separate name for the same brain structure. Yeah. It all does the same stuff, right? Why do I have to call it something different? It really irritates me. It just creates an unnecessary barrier to you guys learning about brains, I think. So that's my take on it. Knocking down barriers here. I want people to learn about brains and create barriers between species. When we learn about a rat brain, we'll call it the same stuff. All right, so here, all that in that nice turquoise, I guess that's that color. That's your forebrain, right? Plus this little bit like down here. So what's not your forebrain? Well, a few things, right? Cerebellum and brainstem, fun pituitary gland. Everything else is pretty much forebrain. So like I said, I don't know what that's like somebody asking like, hey, where do you live? And you go like, United States. I mean, I guess that works if you're talking to somebody like on another continent. But if you're talking to somebody from Milton, I don't know if Tyler really gives them any info, right? Like, hey man, where are you from? U.S.? Thanks. Had that one narrowed down. You want to get that a little smaller for me so I know what's going on? So I don't think forebrain, I don't even think telencephalon is that important. Diencephalon, I mean, there are only a couple things in the diencephalon. If there are only two things in something, why give it another name? I just call it the thalamus and the hypothalamus, right? So it's like this unnecessary middleman level. It just doesn't tell you anything. All right, there's a sulcus. There's a gyrus. That's a giant fissure, right? This is called the temporal fissure there, Sylvian fissure. Got a big split down the middle, also known as the brain's butt crack. It's the sagittal fissure, don't worry about it. You've got however you're looking at that, a left hemisphere and a right hemisphere. Here are your ventricles. That's exciting, right? In this space, if you were to move back, you would eventually start to see the cerebellum and the brainstem. If you don't see that there, it's not a problem. All right, here's the bottom of your brain. How many of you know about the 4 lobes of the cortex? Everybody knows that, right? They actually give you a little bit more information about what's going on because things in the occipital lobe, those are largely concerned with vision. Things in the temporal lobe, a lot of that's auditory. But also it actually does a lot of vision as well in humans and other species. Your frontal lobe, that's a lot of like higher order thinking. And then you can't see it here, but you've got a parietal lobe, and that guy's like an association area. Right? It's going to take sensory information, kind of mix all that together, let you access memories, things like that, so you can have this kind of nice, coherent experience. Okay? That's pretty cool, right? Now we're getting into something that's a little more helpful, I think, with layers or labels, right? So, I mean, here's something that's like primary motor cortex. Well, that's cool. We'll talk about that later. That little strip of your brain actually controls your movements, right? Sends commands out to the world. That's cool. This guy here, primary somatosensory, that's what gets information coming in. Again, we've got primary auditory and visual cortexes, frontal cortex, things like that. But again, I don't want you to spend too much time on this. Okay. Don't worry about that either. You already know the lobes. We did not talk about the corpus callosum. We should talk about that a little bit, right? Anybody know if they have a corpus callosum or they don't? Most people do. Some people are born without a corpus callosum. That's kind of interesting. About 1 in 1,000 people are born without a corpus callosum. Sometimes I've seen as much as 1 in 600 are born acallosal. That's pretty cool, right, Casey? Yeah. They do weird things. You bet they do, yeah. So the corpus callosum is really responsible for connecting the left hemisphere and the right hemisphere. This is pretty important, right? How many of you have ever tried to move your left and right legs? It's important to know what the other leg's doing, right? And so we'll send that information back and forth. You've got memories and processes going on different sides of the brain, and we need to pull that info, bring it together, supply one side with some information, the other side with some info so we know what's going on, right? Now, this is not 100% necessary for your normal, well, it's not 100% necessary for your existence, right? There are folks who will have their corpus callosum cut. Typically, this is folks who have what we call temporal lobe epilepsy. We'll talk more about this later. So if you have intractable epilepsy, try to treat this with a bunch of other drugs and so forth, right? And that didn't really seem to work, and you're having these convulsions, right? When you have seizures, you're having these are very detrimental to your health. Sometimes they'll go in and they'll cut this big fiber bundle here that connects your left and your right hemisphere. That way when a seizure starts in one hemisphere, it won't go over to the other side, right? So it won't go over and start problems on the other side. You guys remember the guy with the dogs and the electrical current, right? So left hemisphere is going to control the right side of your body, right hemisphere is going to control the left side of your body. So if you're having a convulsion in one hemisphere, the other side of your body is going to be convulsing. If we can stop that from jumping to the other side, seems like a good idea, right? So they'll do that occasionally. Now this creates some interesting sort of situations, particularly with some like sensory information about getting from one side to the other. So one of the cool things you can do with these folks is you can like hold up a sign to one side that says eat a banana, and then they'll reach out with the other side and they'll like eat a banana, and then you'll ask them like, hey, why'd you eat a banana? And they'll say, well, I must have been hungry, because the language information they were getting from one side wasn't making it to the other side, so they can communicate that to you. How many of you have ever done something and then you made up a good reason for it later? Happens all the time, right? Okay, happens all the time. There's a big, I mean, man, I hate wading into controversy. I really do. There's like a big controversy that we should talk about. This is an important one, and that's Tom Brady. And I think if I were to ask all of you, no one here, even if you're not a football fan, you have an opinion on Tom Brady, right? You hate him or you love him. And the correct answer is hate. I just want to let you know that. Which I think we've already established in here, right? Correct answer is to hate Tom Brady. But why, right? And this happens with sports teams. How many of you have a favorite sports team? Any reason why? No, right? But you do now, right? If you were to think about this, so who's your favorite sports team?
Like college?
It doesn't matter. Yeah.
I like the Atlanta Braves.
The Atlanta Braves. Are you from Atlanta?
I'm not.
You're not. Okay, so that's great. If you were from Atlanta, that's a different story, right? It's like, hey, you have to be a Braves fan. So why are you a Braves fan?
My family.
Your family. God, jeez. Blank families. Is that a follow your family or a rebel from your family choice?
Follow.
Oh, okay. Because you could have gone either way, right? Often you'll just make an emotional reaction. You're like, oh man, that mascot looks cool, or that guy's name sounds cool, or wow, that looked interesting. And all of a sudden you're a fan, and then you start making up reasons. Well, in the 1990s they were in the World Series or whatever, right? I mean, and you sort of like make up all of these reasons why you're an Atlanta Braves fan, and they're all just based on this emotional reaction you made first, right? And I think, except for me, because I actually have real evidence why you should hate Tom Brady, but everybody else made an emotional decision about that. I'm quite certain. You're just like, yeah, he's awesome, or no, he's not, right? But it was an emotional reaction. You back that up later. You start looking for things, right? And so that's what these folks are doing. You do it all the time, but they do it, and it's really kind of obvious and right there in front of them. Like, man, we just told you to eat a banana by showing you this sign that says, eat a banana. Why did you tell me you were hungry? Because we know you're not. It's like, well, I didn't see the sign. So there you go. So if you ever want to do some interesting things, cut your brain in half. Right, Scotty? They don't do that much anymore. It was more popular a decade or two ago than it is now, but it's still an operation that happens from time to time. Medications are better, other surgeries are better, so we don't necessarily have to resort to that. It's kind of obviously a last-ditch effort, right, for treating epilepsy. That's just showing this is actually kind of interesting. They've sort of mapped out the axon fibers coming out of the corpus callosum. They just kind of show you where all of those are going. It's kind of interesting. Doesn't really tell you a whole lot. Don't need that. Okay. Now, let's talk about some specific brain regions, right? Let's talk briefly about the limbic system. Okay. There are a few important sort of things here. You've got limbic cortex. Most of this is going to be involved with emotion. You've got your hippocampus, which is going to be memory. Makes a lot of sense to pull up those memories, right, if you're trying to process some emotion, right? How many of you have ever had an emotional reaction to someone that you've seen because you knew them, let's say a couple years ago, and they did something really mean to you, like ate your last chicken nugget? I don't know, right? Yeah, that's capital offense right there. So memory, obviously tied to emotion. Amygdala, we really think about this as your fear center, right? We'll talk more about definitely these two brain structures later, but for right now, just know emotions, memory, fear center. We're not going to talk about the fornix or the mammillary bodies. Not too important. If you want to know where these are located, here's your amygdala and your hippocampus, kind of out there in your temporal lobe, right? They've removed, in this case, they've removed sort of the left side of the brain, which is kind of wrapping around here on the outside, but they've left that inner structure there for you to see. Amygdala is actually, amygdala actually means almond, so it's sort of almond shaped if you were to take a look at it. It's kind of interesting. And hippocampus is seahorse. It's supposed to be shaped like a seahorse. These early anatomists were, they huffed a lot of chemicals, and so I think they gave things some interesting names. Okay, so we should talk about basal ganglia. These guys are actually super important, and we will devote a lot of time to the basal ganglia later. Again, we don't really need to spend a lot of time on that right now, okay? Mostly they're going to be involved in motor movement. We already alluded to Parkinson's disease, right? Parkinson's disease, most people think of that as a motor disease, right? It is. Huntington's disease is in that same category, going to involve the basal ganglia. There are other disorders that seem to involve the basal ganglia as well, you might not think of as much. One of those being obsessive compulsive disorder, right? You start to think about the compulsions, right? That's a ritualized, repeated behavior. It's a motor behavior, right? Continued hand washing, okay? It's got a motor component. Autism, basal ganglia is implicated in autism. Lots of individuals who've been diagnosed with autism, they have some sort of stereotypical behavior, right? They'll continue to do. My neighbor a few years ago, when he would talk to you, he would continuously rock back and forth, right? And he would never kind of sit still. He was constantly rocking back and forth. While he was telling me about his solar-powered Christmas lights that he made. Yeah, he would constantly dig through our trash and pull out the electronics components. The craziest thing he ever made is from a gas station, he got one of those those things that cook hot dogs from the inside out. They're like the spears, and they send the current through them. He got a set of those and stuck them in the ground and somehow converted it into like a night crawler device resurrector thing, and it would shock the ground, and the night crawlers would come out, and then he would collect the worms and sell them to a bait shop. I don't know. It was an interesting device. He was a real entrepreneur, I guess. I don't know. Jim was an interesting guy. I appreciated Jim. He would constantly shut my garage door for me, which I tended to forget. I would leave my garage door open most days and drive off, and I would come home, and Jim's like, "Hey, I went in your garage today and shut the garage for you." So he would hit the button and then run out and jump over the trip. Because the little thing, the light beam that comes across. It's like, "Thanks, Jim. I appreciate it." So but again, he had that stereotypical movement, right? And you'll see that. Tourette's is another disorder that involves the basal ganglia. Most of the time, people inappropriately think of Tourette's as sort of inappropriate vocal outbursts, but the primary symptom are tics, right? Often facial tics or other sort of small body tics. And again, it's that movement component that's involved with that. Is why we think about basal ganglia being involved. Okay. Other big structures we should think about is the thalamus. We'll talk extensively about the thalamus when we talk about sensory systems. Essentially, there's a chunk of the thalamus devoted to each sensory system, right? There's a part devoted to vision, a part devoted to hearing, there's a part devoted to somatosensory inputs, right? So there's these different parts, okay? Hypothalamus, we already talked about this. This guy's kind of like the hormone boss. Okay? Basically, it releases a hormone that tells the pituitary gland to release a hormone that tells somewhere else in your body to release a hormone that actually causes you to do something, right? I know that's a real long, complicated process. We'll talk about that when we talk about emotion, when we talk about reproductive behavior, right? Hypothalamus is going to be pretty important for that. There you go. There's the thalamus. Hypo means below, so the hypothalamus is right below that, and you've got your basal ganglia sort of wrapped around those structures, all tucked into the middle of your brain there underneath of your cerebral cortex. Hypothalamus, like we said, it is pretty important. Important for the 4 Fs, right? Fighting, fleeing, feeding, and reproducing. Abby, that usually takes people longer. And not everybody else got it. That's okay. It's okay. We're not gonna add any other comment to that. We're just gonna leave it as it is, right? So those are pretty important behaviors for the again, survival of you individually and of the species, right? So. For those of you that don't know the 4th F there, just ask your parents. Sure, they'll tell you. I mean, that's how you got here, but they'll tell you. Here we go. Thalamus, hypothalamus, pituitary gland, not a big deal. Don't worry about the tectum or the tegmentum. You've got this thing called the superior colliculus and inferior colliculus, not going to be too important. The only thing out of this that's important is the substantia nigra. The reason that's important is because it projects to the striatum. We already talked about that. That's part of the basal ganglia. Why will we talk about that a lot? If you lose dopaminergic cells, we'll talk about that later, in that pathway you develop Parkinson's disease. That's why it's an important pathway, okay? Periaqueductal gray is a little bit important. That's going to be for like pain. We'll talk about that later as we need. The hindbrain. This is something. You've got your cerebellum. Coordination of motor actions. Cool thing about the cerebellum is it lets you know what you just did, right? So you're going to send out a command to your legs. You say, okay, legs, let's start moving, right? And then you need to get that feedback coming in to figure out, did I complete that movement as I meant to? Okay. How many of you have ever been walking along and you've sort of like stepped through the floor, right? This happens to people. Like the stairs are coming, right? And you're not really paying attention and you step and you anticipate the floor, but your foot goes down farther than it should, right? And what happens in those cases? Well, sometimes you fall. Okay. What happens when you don't fall? You have a weird sort of sensation and you pull back, right? Because something wasn't right. That's your cerebellum saying, I anticipated some sort of sensory feedback. I didn't get that. When I don't get that feedback, I send an emergency signal to the rest of your body like, hey, let's hold up and see what happens here, okay? And then you've got some other brain structures back there in the hindbrain. Like I said, that's going to control things like breathing, heart rate, blood pressure, all of those sort of basic life functions, right, that you need to just keep rolling. We're not going to think about that too much, so not really going to spend any time on that today. Spinal cord, stuff goes up and down. Spinal cord is sort of an elevator. I mean, that's really it. Information from the periphery comes in and up. Information from your brain, motor commands, go down and out. That's what I want you to know. Cranial nerves. We don't really need to think about cranial nerves too much. They're kind of fun, I guess. We do want to think, though, about the autonomic nervous system. Right? There are 2 divisions here. We have the sympathetic and parasympathetic, right? These are things that sort of happen automatically. Right? You don't really have to think about this stuff. Sympathetic basically gets you hyped up, gets you wound up for something, right? Parasympathetic is what's going to sort of bring you back down, right? Rest and digest kind of business. Okay? So we've got fight or flight up here, and we've got rest or digest in the parasympathetic. Your cranial nerves, again, don't spend any time on that. And that's actually the end of chapter 3. I told you we'd make it through 6 chapters today. Questions about this? I know that was fast. The reason is because that's a really really sort of an overview of the entire semester's worth of